Okay, which is the laser here? Okay, thank you. To begin with, I want to say what CCL-DUST stands for. It's the Colorado Center for Lunar Dust and Atmospheric Science, and that's the last time I'm going to say it because it's kind of a mouthful. I'm here on behalf of this team. This is a listing of a number of the members of the team. We have a pretty large group with principals, a number of grad students and undergrads even. I want to specifically point out a few people who have done most of the day-to-day work on the Accelerator. Andrew Collette, who's a postdoc in our group, Keith Drake, who's a research scientist in our group, and Anthony Hsu, who's a grad student in the group. So the biggest take-home message of this talk is that we have a working dust accelerator. We're in Boulder, Colorado at the University of Colorado. We've got a big lab. You can actually go to this website, dustcam.colorado.edu, right now if you want, and see an active webcam of what's happening in the laboratory. I suspect not much is happening right now because we're all here, but next week you can see us hard at work. Just some technical specs of what we're talking about with the dust accelerator. This is a Pelletron-based accelerator. The basic design is actually an evolution of the accelerator at Heidelberg, which I think everybody knows, and I actually should point out that we wouldn't be anywhere close to where we are without the continued help of the Heidelberg group. We actually have a very close working relationship with them. This is a 3 million volt electrostatic accelerator. We are accelerating micron scale dust particles of tens of kilometers per second. The upper range of the velocity is actually limited largely by our detection capability, which is improving as we go. We have active selection of particles, which I'll talk about in just a slide or two, and we can accelerate basically any particle that we can charge up. And so to begin with, we accelerate iron particles, but other metallic particles or other particles that can be coated with a metal coating can be accelerated in this facility. The size range that we're talking about is a fraction to several microns in diameter. What you see on the left here is a trace from one of the pickup tubes, which is actually measuring the particles in flight. And this is actually used for selection, active down selection of the particles. But this is a trace which from one of the detectors, which gives the velocity of the particle. This is a 10 kilometer per second particle in this trace, and also gives the charge of the particle. So as we are accelerating these particles, which is a relatively imprecise process, we're actually getting a very high resolution measurement of both their speed and their charge, and from that we can determine their mass. The distribution of particles that we've accelerated so far is given here. This is a mass scale and log scale on the left side on the y-axis, and a velocity scale on the x-axis. But we're covering, again, the range. To begin with, we're covering the lower range of tens of kilometers per second. But as our detection capability and as our sort of black magic of operating the dust source improves, we should be getting up into closer and closer to up to even 100 kilometers per second. What you're looking at here is 4 plots of detectors along the beamline. So this first plot is the very first detector. The second plot is the same particle going through the second detector. From this, we can measure its velocity. By the time the particle gets a few meters down the beamline, we can actually decide whether we want to keep that particle or not. So the user can dial in a range of velocities and masses that are relevant for the experiment and actually dial it in. That activates an electrostatic gate, which can either deflect the particle out of the beamline or admit the particle to the target. And then finally, there's one final detector to tell you right before the target chamber whether you're actually getting the particle that you want. And again, our selection is largely limited by the noise floor of these detectors, which is improving all the time. In addition to the working active down selection of particles just based on sort of basic triggering of these detectors, we also have an active program of filtering so that we can take advantage of the fact that we know the basic detector shape to squash down the noise floor and really detect much smaller and thus much faster particles. This is actually critical to increasing the speed range of the accelerator. This is a pretty busy plot, and I don't really have time to go through it completely, but I just want to say that this is an active area of research. One of our grad students is actually working on this. We're using FPGAs, field programmable gate arrays, to do real-time filtering and real-time selection of these particles. This is largely working. We haven't implemented yet, but it's a work in progress. And the key point here is that we can reduce the noise floor, or reduce the usable signal-to-noise ratio of these particles that are going through to something like 0.25. And so from a functional point of view, if you want to actually trigger off of a somewhat noisy and very quiet signal, we're talking about particles with tens of thousands of electrons or maybe even less. This can be very, very useful and really squash down the background noise. And we think that this can actually be quite usable not only for the accelerator, but any sort of in situ measurement, which is, of course, subject to background electronics noise. Now, on to the science results, which was the title of the talk. We've done just a handful of science experiments since we've been up and going, which has just been this year. The first set of experiments was actually led by Doug Curry, coming over from the University of Maryland, looking at impact effects on retroreflector faces. So here you can see the retroreflector array. Each one of these little dots in here is one of these retroreflectors, corner cube type retroreflectors, and so the issue was to study the damage to the silica faces from dust impacts. This is an electron microscope image of one of the impacts. You can see the scale here is 1 micron, this little line, so this is about a 1 micron impact with cracks. The bottom line of these results were that the impacts were detectable, but these were not really considered to be showstoppers for retroreflector applications. And of course, you can talk with Doug Curry about the details of this. These will be followed up with higher velocity tests as we're able to supply those faster dust particles. Another set of important science experiments which has been done so far is looking at these very thin silicon nitride windows for the Solar Probe Plus. So in this experiment, they're expected to be subject to very, very high moving dust particles. And part of the development of the Solar Probe Plus were these very, very thin windows. In order to test this, we fired dust at them and actually began by looking at both the silicon nitride windows and aluminum foil stacks. One of the worries was that the impacts would actually peel up some of the coating. And as of yet, there are, if you look at this, that wasn't what I wanted. If you look at this plot right here, you can see the dust impacts, and looking at these under the microscope, they've not seen any peeling up yet. But again, these will be followed up by higher velocity dust impacts as we get the machine running at higher performance. In addition, there are ideas for using thin films, stacks of thin films, as dust detectors. So looking at the penetration profiles of these thin films. And we've carried out a number of these experiments so far. This is a microscope image of the penetration through one of these thin films. And in addition to just looking at the impact and tracking what the holes look like and how far the holes penetrate, we're actually able to do a chemical analysis using the scanning electron microscope. So on the left side, you can see that in this box, we're able to get a spectrum, which this line actually just shows the characteristic aluminum line of the background target. But if you look right up next to the hole, in this sort of plume that looks white in the microscope slide, you can actually see traces of the iron particle and even the iron oxides that were on the, presumably on the surface of the particle. And so you can see evidence of that. So this opens up the door to all kinds of new studies, not only looking at the damage that was done, but looking at the particulars of what is ejected during the impact process. Finally, I should mention the lunar dust experiment. There are other talks on this instrument, which is going on to the LADI mission. This is a dust instrument going on to the LADI mission. The PI is Mihai Hirani, who gave the last talk, and Zoltan Stranovsky is heading up this as well. This is the LADI instrument actually in the Accelerator. This was actually just done a couple of weeks ago, calibrating using the Accelerator for dust impacts. I'm actually just going to fly through this slide because I'm running out of time here. The bell has gone off. But we're actually able to get complementary calibration curves. This has in the past been done at the Heidelberg facility, and now we can do this just right here at Boulder. The timeline for this, like I said, this has just come up very, very recently. January 12th is when the Pelotron was delivered. We had our first accelerated dust at the end of February. We've done a number of experiments through May and June. We have some other experiments coming up in July and on into the fall from our own group. But one of the take-home message that I want to leave to this group is that this is a unique facility here in the United States, right here in Boulder, Colorado. All of you should think of ways that you can take advantage of this. And part of our charge in being part of the Lunar Science Institute is to provide a facility to the lunar science, the greater lunar science or space science community. And so we are up and running now, so people should take this seriously and think about ways that we could help your research. Thank you.
Thank you, Tobin. Yes.
This is a very interesting facility. Can one bring one's own, vacuum impact chamber for an instrument, and attach it to the end of your beam line, or does it have to be?
Absolutely. I mean, we certainly will have a review process for anybody coming in and using the facility, and we try to provide. We've got a number of vacuum chambers that are available. Our only requirement is that none of the equipment gets damaged, but we're certainly open to bringing in all number of other kinds of targets.
And can the beam actually be deflected by some angle up or down, depending on what kind of?
It can't really. We have plans, perhaps in the future, to simultaneously or switch out an ion beam, which could be deflected. But the dust particles are really just basically too heavy to be deflected.
How high is that beam above the floor?
It's 1.5 meters.
Thank you.
So just this high.
So what velocity ranges do you think you can get beyond the 100 kilometers a second?
Well, that's a good question. I mean, like I said, the accelerating voltage is fixed, and so essentially what you're looking at is the charge to mass of the particles and whether you can detect them. And so after we, at this point, I would say we're not going to be able to exceed 100 kilometers per second immediately, but as we get our filtering techniques, the usability of very high velocity particles is limited by our ability to detect them. And so right now, the upper limit on speed, which is coincident with the lower limit on charge, is limited by our detector. So as we implement this FPGA filtering, hopefully we can increase that quite a lot, but I'm not ready to really say right now.
We have time for one more question. All right.